So in n-type material, we know that free electrons n0 is greater than the number of holes in the material. So n0 greater than p0 means there should be more probability of finding electrons in the conduction band than finding holes in the valence band. So we should have more probability here and we should have less probability here. So we can visualize that by moving our Fermi level closer towards the conduction band. So if it moves closer to the conduction band, if we zoom further, let's see here. Now we can see here the probability of finding electrons in the conduction band have really increased and that at the hole have decreased. So we can say that in n-type material, Fermi level lies closer to the conduction band. Now let's take a look at p-type material. In the case of p-type material, the number of holes in the valence band is greater than number of electrons in the conduction band. That's for p-type material. So by following a similar argument that we have done for n-type material, we can say that now the Fermi level should lie closer to the valence band. So as we move the Fermi level closer and closer to the valence band, we can see that the probability of finding holes in the valence band have increased. So let's take a closer look. So we can see that if we move the Fermi level further closer to the valence band, we can see that this probability of finding holes increasing. Similarly, the probability of finding electrons in the conduction band decreases. So we have seen that in the case of intrinsic material, the Fermi level was around the middle, and in the case of n-type, it was closer to the conduction band, and in the case of p-type material, it was closer to valence band. So Fermi level is a natural reference point in our further discussion. We will see that how Fermi level becomes useful in calculating the carrier concentration in a material. So let's see some of the important notations we will be using in the coming discussions. So in order to represent the energy level corresponding the top edge of valence band, we use EV. So EV corresponds to the top edge of valence band. So this top edge, we use the notation EV. So we may not be drawing band diagram completely, but we will be using EV to represent the top of valence band. And in the conduction band, the bottom edge of conduction band, we use EC to notate the bottom edge. So this is EC. Fermi level, we use EF. And if we mention specifically about intrinsic material, we use EI. So EI, we use it for intrinsic material. And we use EF for general case. In any discussions, if we want to talk about n-type and p-type at the same time and needs to compare them, we may use EFN to represent Fermi level in n-type material, and we may use EFP to denote Fermi level in p-type material. That is, EC is the bottom of the conduction band, EV, it's the top of the valence band edge, EF we use for Fermi level, EI, the Fermi level in intrinsic semiconductor. If we want to specifically talk about n-type or p-type, we may use EFN or EFP. And we will be using EG to represent the energy gap. So this is our energy gap, EG.